326, it's WGS 86, it's geographic coordinates. So that's perfect. So let's look at, we will come back to that again, but let's look at another data set with other types. I have also from Natural Earth a shapefile with all countries. Actually, it's admin 0 countries. This means it's just on a global level. For example, United Kingdom doesn't have England, Scotland, Ireland included. So it's just United Kingdom there, so admin 0. And Italy doesn't matter, just Italy as admin 0 country. So we can also check the first. You see, I made a semicolon here because this one is a polygon, and a polygon contains many points. You see, it's really big. You shouldn't print this actually. This one is the polygon of the first country in the data set. It's just the first country. Multi-polygon, so I don't want to see that. No. This is cool in JupyterLab. You can just close that if you don't want it. And just let's look at the name. It's Indonesia. It's just the first. It's just random. It's the first data set in this. It's Indonesia. We can look at the name in Chinese. It's this one. And we can look what continent it is. It's in Asia. And we can look at the population in this data set. So Indonesia, according to this data set, has 260 million people in 2017. So let's look at Italy. Again, I go through the whole data set. I check if the country is Italy. And then I just print the properties there, and I save the geometry in variable geometry. That's the polygon, actually. So let's do that, and we see Italy has 62 million, is that correct? I've never counted it myself. Also in 2017, and as we expected, it's a multi-polygon. Yeah, because we have multiple polygons, as I mentioned before. There are actually not many countries which are not multi-polygons, by the way. And I can create from Shapely, from this coordinate list, I can create a multi-polygon. Just import the multi-polygon and create this Italy, and I just plot it. And you see, that seems correct. I don't see the hole at the Vatican, it's too small, but it should have one if you zoom in. But there are different, I think there's another enclave somewhere in the north, but it doesn't matter. So now we want to do an advanced thing. I want to go through the airports dataset, and I want to print all airports which are within this polygon. And now is the amazing part. This can be done with only 5, 6, if you never count the imports. So we can do this with 5 lines of code. So you open this data set. Actually, in the afternoon, we will see this is possible in 1 line of code, I think, with GeoPandas. But so you open the airports data set and look at the position of this. And I check if this position of the airport is within this Italy polygon. Then it prints this IATA code of the airport, the name of the airport, and the coordinates of the airport. So let's see if this works. Yeah, it actually works. And we see there are some airports here. As I mentioned before, this list is not complete. There are some smaller airports which are not in this data set. So it's a problem of the data set and not a problem of the algorithm. But that's what you get with open data. These data sets are usually cost a lot to have all airports, all data, but it's okay. Another thing is you could take OpenStreetmap data. I didn't want to do this today, but you can export it from OpenStreetmap and have all airports, and then take these which are actually better than these Natural Earth data sets. But the problem is with OpenStreetmap, it's really huge, so I can't just put it on GitHub. So that was the reason. And also, let's do another thing. I want to get all places in Italy with the same approach, which have a population of more than 100,000. So again, I open the populated places file. I get the geometry of this place, of every place. I make a point of it, and then I store the name of the place and the population. I convert it to integer. This is not really necessary. Fiona does this automatically, but I still do it. It's just more stable. It's automatic detection, but sometimes some data sets are wrong and have some bad number, not a number, then this will actually fail. So you should make an exception here, catch it. So I say if population is bigger than 100,000 and the position is within the Italy polygon, then print the name, population, and position. So we see, yeah, it's a, of course, Rome should have many, Milano has, sure, and Trento, has Trento more than 100,000? Trento, yeah. Trento is just at the limit, 107,000. So yes, it's inside. Okay. So you see, we can really do nice things with this Fiona library. It's quite easy. Of course, we can even do more complicated things, but this is just the beginning. It should be a introduction tutorial to these things. And in the afternoon, you will see how you can do the same with GeoPandas, which is even more easy. I would like to show it now, but but let's wait. No, it's okay. I'll let you. Yeah?
How do you get the list of, when you open this C object, when you can access as a dictionary all the different features, but how do you get the list of available features?
Usually this is documented. There's a text file with all properties inside. And if you don't know it, I would just open the first and look at it. But usually it's documented. It should be documented, actually. But if it's not documented, just open the first, print it. That's what I do. Or wait for the tutorial this afternoon and use GeoPandas, and then you see all attributes in a really nice list. I would really like to show it now, but let's wait. Which makes it even more easy. Okay, but one thing GeoPandas doesn't offer yet, I don't know if this is planned, is raster data. Raster data is very important. You have on one side you have aerial imagery, satellite imagery, and these things, and also you have elevation data. So you can have for every point, for example, you have the elevation value. If you take this, you can create a 3D model of the terrain, and you can render this, whatever. Can do analytics, can see from this point to the next point, is there a mountain in between, and so on. So that's where Rasterio is handy. Rasterio is based on GDAL, which is a C++ library, which has its own binding, Python binding, but it's really, it lacks a documentation. Actually, the documentation there is the C++ documentation, and you have to guess the Python functions, more or less. There are some examples there, to be fair, but it's not. It's just C++. You open the data set, you have it's just not Pythonic, you know what I mean. And then Rasterio, it's developed by Mapbox, and they try to create an interface which is more in a Pythonic way. So the most important function in Rasterio is open. So you open a data set. I'm limiting myself today of reading data sets. You can also write new data sets, but that's not very interesting for an introduction tutorial. So I open this, and you have different options. It's the complete list. You don't need to use all. One interesting thing is the driver. there are different formats, JPEG, GeoTIFF. If you want to see the list of all supported drivers, you can go to the GDAL homepage, if it works, yeah. And here you see the supported raster formats. It's 155 raster formats. And you see there are many such raster formats available. So just random. You see, it's really huge, and these are all supported. You can also directly access from databases some formats, and there are really some exotic formats. NASA Planetary Data System, I never used that, so but you see, that's all available. So it's quite cool. And one important thing is, if you have raster data, we have different channels. So we can, for example, have specular imagery. You can have infrared. We can have many different bands, it's called. And what we are looking today is just RGB image. We take this blue marble dataset from NASA. It's actually an image. I don't know if it actually works to open it in the. It should work. No, it doesn't work. It's not. It's GeoTIFF. Okay. It's not really TIFF, so it doesn't matter. It's just the whole Earth, what we saw actually before. We will plot it later, so you can imagine that. So I just open it. R for read, you can omit that. R is the standard, like in the normal Python, open. And then you can print different things of this data set. For example, a name, okay, that's just a file name. The mode, you read this. And now the most important count. This data set has 3 bands. So it's RGB, red, green, blue. Some data sets, as I said before, they can have 7, 8 different bands, spectral, infrared together. So it's quite interesting. And here the indices, it's 1, 2, 3. That's in 99% of the cases you have raster band 1, 2, and 3. But in theory, this could be different. You could name it 5, 10, 11. So, but no one actually does that. Then the width and the height of the image. We have 3,600 pixels width and 1,800 pixels height. And very important, the coordinate reference system. We see this one is also EPSG 4326. That means WGS 84 geographic coordinates. And now the very important thing is the affine projection. It's actually a matrix where you can use to calculate geographic coordinates in pixel. Or not only geographic coordinates, I have to say the coordinate system of the data set to pixels and in the other around. And that makes it really easy. In the original GDAL implementation, you don't really have this. You have to create your own functions to calculate this. And in the rasteria, you have this included. And you can actually say, OK, 0, 0. The pixel 0, 0, that's top left. And the top left pixel in geographic coordinates is minus 180 and 90 degree. So this makes sense. I think you know that. Hopefully you know how it's geographic coordinates. We have something like this. And here is the longitude. So the longitude is from minus 180 to plus 180. And here the latitude is from minus 90 to plus 90. So before we looked at this 0, 0 pixel, so it's minus 180 plus 90. So it's quite. And to do the inverse of that, you just make this tilde, and you have the inverse of this matrix. I can show that. It looks like this. And what it does is just the contrary. You have 0, 0. I go back to my nice image here. 0, 0 would be in the middle, here in degrees. And in pixels, it should be in the center of the image. So let's look if this works. 0, 0 should be 1,800, 900, and we saw the width height is 3,600, half is 1,800, and 1,800, the half is 900, so this seems to work properly. So let's look what pixel is Trento with our previously introduced coordinate. And as you see, we use the longitude first and then the latitude. And we print the pixel coordinates. It's 1911, 439. I store this as px, py. So remember this, we will use that later. This is our Trento coordinate. Also the bounds of the data set, we see the bounding box, we have the whole planet here from minus 180, minus 90, 180, plus 90. So we can also print the bounding box. So let's use matplotlib to actually display this. So what I have to do is import matplotlib, and I also use NumPy, because the results of this read dataset is also a NumPy. It's always a NumPy array, just for performance reasons. So I read the 3 bands, RGB, and then for plotting I have to put them together. And there is a nice command in NumPy called dstack, where I can just put them together in one big matrix. See? So it's RGB of every pixel. It's big. I make this a little bit smaller. No, that's too big. And I just use image show and this array RGB. That's all, and you can plot it using matplotlib. And in addition, I plot this px, py. Remember, that was the coordinate, pixel coordinate of Trento. Okay. I think, yeah, but I guess it's correct, the pixel for that. So, it's on the projection, you don't really see it very well. It's here, this red dot, north of Italy, so it seems correct. Okay. Now, what we saw here is we loaded the whole image, really the whole image, and displayed it on the screen. This was only possible because this image was quite small. Usually we do have multi-terabyte big images, and for that we have to find a way to read this in a certain performant way. So one way to accelerate that is creating overviews. It's something like pyramid layers. Let me show that to you. It's a quite easy principle. You have one image here. That's my image. Okay. And then you create the same image half size. That's half of the image. So first you have 4 terabytes. The next is 1 terabyte. And the next is a 4th terabyte, and so on. Okay, let me make 4. And so you have different representations. So if you want to read an extent of this image, you first take the small one, and then you check if there are enough pixels for display this on the screen. A screen is typically, in this case, 1000 to 24,768. So if this is enough, we can take a smaller representation and read this. And if you want more information, we always go up to the bigger. So that's called overviews. I copy my data set to a new location. I call this blue marble resampling because it will modify the data set. And then I want to see if this data set has overviews, and we see no, it doesn't have overviews. So it's really slow, this data set. Okay, it doesn't matter because it's small, but it doesn't matter. And there is a command in Rasterio called build overviews, and then you specify 2, 4, 8, 16, 32, 64, and so on. I make 4 overviews. I say use average or nearest neighbor or whatever for resampling. And update this with using Rio overview. That's inside TIFF. You have to do that. So if I do that, and then I check again the overviews, we see we have these overviews here. Every band, red band has this, the green band has this, the blue band has overviews now. So what I can do is I just read a part of the image, or I read the whole image with a lower resolution. So let me read the whole image in a lower resolution. I say the fourth of the height of the image and the fourth of the width of the image. I read it again in RGB. Now, of course, it's much smaller. And I will plot it again with matplotlib, and we see it looks the same. Because, yeah, in this small resolution, we don't have a loss, but it's only a fourth or even less of the memory. So if you would have a 10 terabyte image, this is the only way to actually display it on the screen. We don't want to read every pixel and then display it on the screen. So overviews are really important. And if you create a data set, or if you download a data set, the first you do is create an overview so you can actually display it on your screen. So if you read every pixel and then display it, you can wait 10 hours before you see the whole image. Or before you run out of memory even. The second thing, we still have 50 minutes, is correct? No, okay. The second thing is we can just read a part of the image. So I specify the pixel coordinates I want to read. And I just say I want to read the window, this window for red, green, blue. I stack it again, close it, and then display it using matplotlib. And we see this is a window to read. So we also see that the resolution is not really great of this image, but it fits on GitHub. Okay. So now we come to the next part. Now we come to the OpenStreetmap part I promised you earlier. A really cool Python module is Folium. It's based on Leaflet. Any one of you heard about Leaflet.js? Quite a few. It's a mapping library. It's actually this one. It's used in OpenStreetmap for display these maps. That's Leaflet.js. And Folium is a Python module creating JavaScript code in background. We never see it. Actually, we can save it to a HTML page with automatically created JavaScript code. So all I have to do is import Folium and then create a map. I say the center of the map is, in this case, it's in Switzerland, Zurich, and zoom level, and M, just display it in the Jupyter notebook, and we see Zurich, Hauptbahnhof, center of the world. Yeah, in this case at least, it's the center of the world. But I could have done Trento. I will do that in an instant. We can have different tiles. It's called tiles. In OpenStreetmap, you can have your own styles, for example. If you know Apple Maps, they just take the OpenStreetmap tiles and apply their own style. Or Mapbox, you can create a custom style. There are some embedded styles, like Stamen Toner, which is just black and white. I think the network is too slow. You see, it's just a black and white map. Sometimes that's enough. It should be around, it's too fast, but doesn't matter. Or there are Mapbox pre-rendered tiles, more a bright map. Now the network is too slow at the moment, but doesn't map. There is also Mapbox control room, the classic OpenStreetmap. I don't open it now. And and so on. You can try it when you have a faster internet. There, I made a link. It's a little bit outdated, but they have some different styles there. You can also embed Mapbox, your own things, but then you need an API key. Also MapQuest, but there you also need an API key. You can also you can even use Google Maps and other ones, but for these you need your API keys. So I don't show it here. Yeah.
Can you change also the projection system? Or
No. This one is only available in the Mercator projection. The reason for that is for one, it's nice because it's a quadratic view. If you look at it, you can map it. You can limit it to 85 to 85 in latitude. And then you get a more quadratic way to look at it, and then you can tile it in a quarter tree. That's the main reason. And the second reason, it's conformal. So if you zoom in and you have aerial images, for example, you don't have distortions because the angles remain the same. The size changes, but the angles remain the same. So a street is correctly displayed from the angle. In the latest version of Google Maps, if you zoom out, you see the planet. You see a globe. The reason for that is because many people were confused and were thinking that in the Antarctica you can fit the whole world inside and so on. So.
The part that is in the center is not distorted, right?
The local part is not distorted in a yes. If you don't compare it to another place, it's not distorted. Yes.
So if I, for example, if I switch the map to like from Antarctica in the middle, so
yes.
it will be the opposite, like the equator will be distorted, right?
No, in the Mercator project, nothing is distorted. It's just the size is wrong. Yeah, of course. In the whole, it's a distortion. But if you zoom in to the penguins here, then this is correct. This is in a certain way a metric system. So it's.
You zoom out, but you make the Antarctica the center. The Antarctica is correct, and the rest is.
Yeah, exactly. So here is locally it's correct, but if you compare it to another place, then it would not be correct anymore.
Zoom out, stay there and zoom out and see how if Antarctica gets smaller and the rest gets bigger.
Exactly. Yeah. So this one is not correct anymore if you look at the whole planet. No, it's too slow, but you get the idea. Okay, let's continue. We only have 9 minutes. So one cool way is you can in Folium you can add markers. It's some point of interest. I stayed in Zurich for the moment. I make 2 hotels here. You can make pop-ups with text inside. You just write inside what's this pop-up, and inside is a string. Actually, you have to be careful here. It must be HTML compatible. You can't have. We will see that later. You can't have special characters inside. You can change the icon. I don't do it with help Folium icon. You get all possible things. One way is using the font Awesome. It's actually a font, which is quite common, which is used to create your custom icons. So I create 3 hotels again around there. I say the color is red, green, and blue. And I say a prefix is font Awesome, and the icon type is hotel. Font Awesome, if you go to the web page there, you see many of these icons. You can just type the name here of this, and you get, as a result, you get the icon representing a hotel. You could mix it up with different things, but this is the result. One thing, you can just save that. If you say M, I didn't write it here, but if you say, this happens when you try to live code, you can just save, output, HTML, and then you get a HTML page which is exactly the same. So it should be inside here. No, I'm in the wrong folder. See output HTML, you can open it. This is the HTML. You can open it in the web browser and you see the map. Okay. So let's go on. Let's make a combination of all these things. I take Fiona, I take the populated places again. And this code we already know. This one took the places which are more than 100, population with more than 100,000, and the position is within the Italy polygon, multi-polygon. And then if this is the case, I just store the longitude and latitude and create a volume marker. And also I check if the name is Trento, I make a green marker, and if the name is not Trento, the marker color is red, just for fun. And here we see two important things. First, in volume, we have first the latitude and then the longitude, contrary to before. There are two fractions in this world. Some people say first latitude, then longitude. And the second fraction says first longitude and then latitude. I'm personally in the fraction first longitude, then latitude, in the sense first x-axis, then y-axis. But at the end, it doesn't matter. You just have to know which framework uses which. And as pop-up, I use the string population and the name. What I omitted to tell you is, no, this is okay, it's not yet, we are not yet there. So we see, yeah, the resolution is not that great, but you see the green is Trento, and here are all the population numbers of the places with more than 100,000 population. So you really can create a fast map like this with a few lines of code. And we can also add shapes to this map. For example, we take this Italy shape, multi-polygon we had before. All we have to do is use volume GeoJSON and use this Italy polygon, multi-polygon from before. This is all. So it's the same code like above. I just add volume GeoJSON and add this Italy polygon we extracted before from Fiona. And also I added here a lambda function which defines the style. This can be quite interesting. You could also create lambda functions of the fill color and every part here. And you could really do some selective styles for each feature there. So you could have for every place a different style, for example. So let's look at that. And we see now we have the Italy polygon, green, and the places. Isn't that beautiful? And we could see if this now we don't have time for that, but you can check if if the Vatican is really not filled. Probably not, because the data set is simplified, so and the Vatican is too small, so maybe it fall away. We have 3 minutes left. Let's come to the last example. This one is just a quick example. I show you how to access live data and put it on a map. So one of my favorite live feeds is the earthquake dataset. The USGS creates a GeoJSON, and you can access past hour, past day, past 7 days, all earthquakes. And you can say, I only want to see the magnitude 4.5 and higher earthquakes. And that's a GeoJSON collection, and here you see these. So what I do here is I choose all earthquakes bigger than 2.5 magnitude from the past week. So from last week to now, or to the point where I execute these files. I use requests and get this URL and store it as a file. I store it as earthquake GeoJSON. I write it and close the file. It just downloads the file and stores it on the hard disk. So you see here is the file, earthquakes, GeoJSON 1 second ago created. And now I use Fiona and go through this file. I open earthquakes, GeoJSON, read it, and go through all earthquakes in this collection. I get the geometry. It's actually a point again, where this actually is a 3D point. We have a set coordinate too, elevation, where this earthquake occurred. And I store the position, and I store the magnitude, and they also give a title. Every earthquake has a title. Usually it's automatically generated from the next surrounding. So I check it. If magnitude is bigger than 4.5, I store the longitude, latitude, elevation, and just print it. Let's see what happens. This is live. This I couldn't try before. So we had here a 6.2, Indonesia. And yeah, that seems to be the biggest. Oh, 6 here, Iran. I didn't print out the time. We could also print the date there. But for time reasons, I didn't want to make the date because you have to convert it and so on. It's a bit complicated. You see, this is the list of earthquakes. And now I just do the same and create a volume map of it. So I make a center 0, 0, center of the Earth, create a volume map, zoom level 2. I open again these earthquakes, do the same. If magnitude is bigger than 4.5, I take this longitude, latitude. Elevation is not really important. And then just to show there is a circle marker in volume, or just a marker which is a circle, where you can also specify the radius. I just take the magnitude as radius. And then something very important is, I mentioned it before, you have to HTML escape the title. You know, in URLs or in web pages, you can't use all characters. So you know this ampersand and these things. So I have to encode it, or it will not display correctly. And then I say pop-up is a title. I fill it with the color, fill color. I say opacity 1, so it's not has no opacity, and add it to the map. So let's look if this works. And we see, here it was a bigger, smaller, and here is our earthquake map.
You see where the cross
And
like the earthquake areas.
for example, here we see, exactly where you can see where it was. But it's only magnitude 4.5. You can change the code and make it less. And here. And this text is really automatically generated, I think, from the service. We saw in Iran there was bigger earthquake, magnitude 6. So this is. But of course, it would be nice to have the date of the earthquake embedded. But for time reasons, you see, it's just finished. I couldn't do that anymore because you have to convert the date. Okay. Okay. Thank you very much for your attention. And don't forget in the afternoon, GeoPandas, one of the greatest libraries for geodata.
It's very interesting. I have a last question if I can.
Yeah, sure.
Can you also put a raster on top of this, or it's only for point and polygons? Because I have.
You can add raster layers if they are in the Mercator projection. You can also add.
Projection,
yeah.
and then I can.
You can have WMS, WMTS server, and get this even from the server.
Because I have those offline.
Offline.
And they are
offline is
WGS84, so you have to convert those in Mercator.
You need this one tool, GDAL 2 times, it's called.
Okay, so it's because I'm a bit for this work. I'm actually working with R. There's a lot of nice things, but I would like. But the main work I do is in Python, so I was switching everything in Python. I want to see how complex it is.
So GDAL 2 tiles is also Python script. Where you can create tiles from Rust. So if you have any Rust data with georeference, you can just create tiles in the Mercator projection. And then you can embed this to the...
But why do I need tiles? Can I also convert my complete data set in?
Now you need tiles for volume to work. You need tiles.
Tiles, so means it's kind of a rectangular area, because I have the whole Europe with air quality concentration, so it means I have to cut this in areas.
But this will make it automatically.
Okay. So how many tiles you produce? Well, that's not important.
It uses usually many, but you can specify how many zoom levels you want, and
because it's very nice this way to show results. So I was wondering.
This one is practically only the easiest way to create tiles.
Okay. So in GDAL you also have a collection of Python scripts or Python tools. It's not only
What
C++.
I do, actually this one is should be included if you use Anaconda and GDAL. I fear this.
We have to start.
Oh, it works. So you can just you have Anaconda, GDAL 2 tiles. And then you have to, I don't know here the parameters, the input, exactly. No, I think you don't have to write Python, just the tiles. And then